welcome everyone. I hope you all are well and healthy. It's a pleasure to me today to welcome you to the online Materials Research Laboratory webinar series. And just letting you know that please enter your questions on the chat window during the webinar, and they will be answered at the end of the talk when we'll try to get to most of them at least. It's my pleasure today to introduce our two speakers, Dr. Tao Shang and Jeffrey Grau. So Dr. Tao obtained his PhD in electrical engineering at Brigham Young University. He has about 15 years of experience in micro and nano fabrication. We are very fortunate to have him working as a research engineer at MRL MicroFab since 2010, where he is in charge of various instruments in our facilities, including the Wraith e-beam lithography system, the Temescal e-beam evaporator used for metal deposition, and a couple of AJA instruments, the e-beam evaporator for oxide deposition, and an AJA sputter coater dedicated to metals and oxides. Jeff Grau, with over 40 years of experience in mask making, started his career at General Instruments Corporation in New York, where he worked as a Photomask technician for over 8 years. And then he relocated to Commodore Computers, Pennsylvania, where he worked as a lead technician for 8 years. He then relocated to Advanced Reproductions in Massachusetts, where he worked for 19 years as a Photomask manager. Jeff followed his dreams to work in academia when he relocated to Purdue University, Indiana, and worked as a research engineer for 8 years there. Then we were really lucky, and he decided to relocate to the University of Illinois and join us as a research engineer where he is now. So Dr. Tao and Sir Grau will talk about micro and nano lithography. And I would like also to bring your attention to the next webinars that we'll have on the same series. The next one being on next Thursday will be given by Dr. Zweig about an introduction to transmission and electron microscopy. So without further ado, I'll join me welcoming Jeff and Tao.
Thank you, Julio. Hi, my name is Tao Shang, and welcome to today's MRL webinar series. Today's topic is about micro and nano lithography, presented by me and my colleague, Jeff Grau. We're both research engineers at the Material Research Laboratory at the University of Illinois, Urbana-Champaign. Here, please take a look at the map of the MRL major cleanroom. This is basically the introduction to the cleanroom area. As you can see, 313 is the gowning area where you need to get gowned up to get into the cleanroom. Well, why do we need to get gowned up? Because we need to keep the cleanroom clean. From its name, we know that the cleanroom is a clean area for micro and nano fabrication processes. The cleanroom is actually categorized by a level of particles. So the maximum amount of particles larger than 0.5 micron per cubic feet is the standard. So our cleanroom is classified as class 100, which means that the maximum number of particles larger than 0.5 micron is 100 per cubic feet. The corresponding ISO standard will be ISO 5, which means that there will be about the maximum amount of particles larger than 0.5 micron in 1 cubic meter is 3,520. After getting gowned up, we can go to the clean room 388. When gowning up, we need to wear this bunny suit. This is actually the protection from us further contaminate the clean room, because people working inside the clean room is the major contamination source. 388 is the lithography room, where houses the photolithography tools called aligner. You can see we have Carl Su's MJB3 and MJB4 aligner. And also there's a Heidelberg MLA 150 aligner. This one is a maskless direct writing system. And you must have noticed that 388, 384, 359, and 387 all look yellow, because the chemicals, in most cases, the photoresist that we use in the process of photolithography are sensitive to UV light. So the clean room actually filters out all the wavelengths shorter than blue. That's why the whole clean room area looks yellow. 384 is the sample cleaning and the developing room. We can clean our sample prior to the lithography. We can develop our sample after the lithography. We do these jobs in developer hood and the solvent hood. Across the corridor, 359 is for acid etching. As you can see, there are several hoods for acid etching. We supply acids such as hydrochloric acid, nitric acid, and the phosphoric acid. We also supply HF and BOE, hydrofluoric acid, buffer oxide etchant for silicon dioxide etching. Nanostrip is also used in our clean room. We have a separate hood designated for nanostrip. So these acids are dangerous. That's why we do the acid work in the hood, and we also wear PPE to protect ourselves, and safety precautions should be followed. 387 is a metal etching room. Also, we have some UV flood exposure system and the PI oven here. The metal etchants we supply are versatile. We supply a gold etchant to etch gold. We supply a titanium etchant to etch titanium. And you can see that the metal etching work is also done in a hood because of the nature of the material we are handling. So we need to wear PPE, and the extra safety precautions should be followed. It should be noted that this clean room is not the only clean room we have. There's another smaller clean room called the race prep room. It's designated for the e-beam lithography process. Also, not all the instruments are inside the clean room. Some tools are outside due to the nature of the tools and the needs of the users. Here are the basic concepts of photolithography. Suppose you have a silicon dioxide covered silicon substrate, and you apply photoresist on top of the silicon dioxide. Then you can shine a beam of UV light through the photomask onto the photoresist. Photomask is just a slab of glass, and part of it can block the UV beam, and part of it can let the UV light pass. Upon the exposure of the UV light, the photoresist will go through some chemical reactions in the molecules. Depending on the type of the photoresist, you can create different patterns. If the photoresist is positive, it means that the portion of the photoresist exposed to the UV light will be dissolved in the developer. So you end up with a pattern like this. If the photoresist is negative, then the portion of the photoresist exposed to the UV light will remain after developing, and you end up with a pattern like this. Now we have successfully created the pattern, and we replicated from the photomask to the photoresist. But that's not the final goal. We want to replicate the same pattern into the silicon dioxide layer. So the photolithography process here is just an intermediate step. After the developing, we need to etch the silicon dioxide using the pattern we created here as an etching mask. So we just simply use hydrofluoric acid to etch silicon dioxide, and we end up with the pattern in the silicon dioxide after the photoresist is stripped, because the photoresist is no longer needed. Here is the complete list of process steps. Let's just start with substrate cleaning. The purpose of a substrate cleaning is simple, just to remove the contamination. And when you open a box of wafers, no matter how clean they look, you still need to clean it. We just run a simple cleaning process here. First, we rinse with DI water to remove dust and larger particles on the substrate. Then we can rinse the sample with acetone to dissolve organic compounds. Then we rinse the sample with isopropanol alcohol to clean the acetone. Afterwards, we just blow dry the substrate with nitrogen gum. Because of the volatile nature of acetone and the IPA, we do this work in a bench or hood. Oxygen plasma etching, or oxygen plasma disgumming. This basically works to remove the organic thin film and the residue. And oxygen plasma etching is actually oxygen plasma etching. Basically, oxygen plasma will burn off all the organic compounds on the surface of the substrate. And the oxygen plasma cleaning can be done in this Herrick plasma PDC-32G cleaner. And it can also be used for photoresist disgum or stripping. Nanostrip cleaning. Well, nanostrip cleaning is a very intrusive method of cleaning. If your sample is still dirty and you're not happy with the surface, you can try nanostrip. Nanostrip is actually a mixture of a sulfuric acid and hydrogen peroxide. You can do this in your lab. You can mix the sulfuric acid and the hydrogen peroxide together. However, mixing these two chemicals together is an exothermic reaction, which means that it will generate a lot of heat, and you end up with a bottle of hot bubbling acid. Obviously, it is dangerous, so we turn to nanostrip. Nanostrip is actually the commercial version of the mixture, which is called Piranha. It's more stable, and it's much safer. The purpose is simple. We just use nanostrip to remove organic materials like photoresist, oil, grease, things like that. However, it should be noted that nanostrip itself is a very strong oxidizer, and it's a strong acid. So you need to wear extra PPE, and you need to follow extra safety precautions. That's why you can see it's done in a hood. Also, you need to make sure that you don't create any violent reaction for a nanostrip. Of course, you don't want to, spill. You don't want to squirt some organic compound like acetone to nanostrip. You don't want to heat it too much and pour it into the waste container, things like that. Also, some metal surfaces cannot handle the nanostrip cleaning, for example, like aluminum, because the etch rate is really high. HF dip. Well, the purpose of HF dip is actually specific. It's specifically used to remove native oxide on silicon and to create a hydrophobic surface. HF can clean the, or BOE can clean clean the surface of a silicon wafer, because it basically etches the silicon dioxide on top. HF is very vicious. You need to wear the PPE, and the extra safety precautions should be followed. After cleaning the substrate, we can prime the substrate. Okay, so why do we need to prime the substrate? Because we want to make sure that the adhesion during the development and the wet etch is good enough. So before we can start the lithography process, first we need to make sure the surface is hydrophobic. And then we can do the following things to improve the adhesion of a photoresist. We haven't done the photoresist spinning yet. We just want to make sure that we have a good base to start with. You can dehydrate bake the substrate at 100 to 200 C before the spin coating. Say 5 minutes, 10 minutes, however long you want, doesn't matter. You can run oxygen descum using the oxygen plasma cleaner. Also, you can apply adhesion promoters such as HMDS. This is the tool, HMDS oven, we use to prime our substrate. Basically, we use vapor, HMDS vapor to apply on the substrate, and then we bake it at 150 C for about half an hour. It should be noted that the adhesion promoter won't work on all the surfaces. It can only work on oxide surface. So if you have a pure metal surface, say you have a gold wafer or something like that, it may not work. Okay, spin coating. Okay, so spin coating has been used for decades for the application of thin films. A typical process involves depositing a small puddle of photoresist or fluid resin onto the wafer, and then spin the substrate at a very high speed, typically 3,000 RPM to 4,000 RPM. You can see the wafer is spinning here. It's actually vacuum sucked by the vacuum chuck here, which is connected to a spinning spindle. So once the photoresist is applied to the spinning wafer, it can be uniformly distributed along the diameter of the spinning wafer to create a very thin and uniform film. However, at the edge of the wafer, there will be some more accumulation of a photoresist there. So it will create an unevenness in the thickness of a photoresist. It's called edge bead. So edge bead has to be removed or reduced before the photolithography process. The spin coating can be either manual or auto. Here we have a semi-auto system. This is the headway spinner we use for spin coating. The final film thickness and other properties actually depend on the nature of the photoresist, the viscosity, drying rate, surface tension, things like that, and the parameters we choose for the spin coating process, like the spin speed, acceleration, and the time. Of course, the more viscous the photoresist is, the thicker the thin film it can be. The higher the spinning speed, the thinner the thin film it can be. If you want to know the thickness as a function of spinning speed, you can also check the data sheet of the photoresist. After the photoresist spin coating, it's still liquid, so your substrate surface is actually sticky. You cannot work with it. You cannot directly put it in a liner. You need to solidify the photoresist. You need to make it glassy. That's why you need soft bake. Soft bake is also called a pre-bake or pre-exposure bake. And it drives off excess photoresist solvent. It can also relieve the stress in the film, and it can also help promote the adhesion of the photoresist. And we just use a simple hot plate to do the soft bake. The soft bake depends on the type and the thickness of the resist. So the baking temperature and the baking time can be found on the photoresist data sheet. Also, you can tweak the parameters, according to your need. However, you should pay attention to two scenarios: under baking and over baking. If you under bake it, it means that you don't heat it enough, you don't heat it long enough, then too much solvent will remain in the photoresist, blocking the UV light from exposing all of the photoactive compounds. If you over bake it, heat is another type of energy. So the photoresist is absorbing energy then the photosensitivity may be degraded. Okay, now it's exposure. Here I will pass on to my colleague Jeff Grau, who is an expert in lithography. Jeff?
Thank you, Tao. Exposure. This slide represents different wavelengths of light that are achieved from a mercury arc lamp. As we can see, we have a 435 nanometer, which is considered G line. 405 nanometer is considered H line, and 365 nanometer is considered I line. Deep UV ranges from 150 to 300 nanometers. It's always important to check the photoresist data sheet for the wavelength ranges and exposures of the dosage that you're going to use. And we also recommend that we always check the aligner for the last calibrated intensity reading. Now, if you're using a negative photoresist, a post-exposure bake is necessary. Here we have an example of the three different aligners that we have at the MRL. On the left, we have the typical Carl Zeiss MJB3. This wavelength it uses is 365 nanometers. It accommodates a mask size of 3" by 3". The intensity is 10 milliwatts per centimeter squared, and the minimum feature size is approximately 2 microns. We recommend 5214 photoresist, which is either negative or positive, depending on how you want to use it with this particular aligner. Here we have the Carl Zeiss MJB3 deep UV aligner. This differs from the typical MJB3 because it's been converted to deep UV. The wavelength is 220 nanometers. The mask size, again, will accommodate a 3 by 3". The intensity is 1.5 to maybe 2 milliwatts per centimeter square. And the minimum feature size is approximately 1 micron. And we recommend the use of PMMA photoresist for the deep UV. Here we have the Carl Zeiss MJB4. The wavelength is 365 nanometers. It too will accommodate a 3 by 3" mask. The intensity is approximately 10 milliwatts per centimeter squared, and we are able to achieve a minimum feature size of approximately 1 micron. Now, photomasks. The question might arise, why do we need a photomask? Well, a photomask consists of either a very flat piece of a soda lime or a quartz glass. It has a metal coating consisting of either chrome or iron oxide. Iron oxide offers the ability to see through it, and it makes aligning much easier on the wafer. Both metal coatings will block radiation at the desired wavelength, allowing UV light to be transmitted where needed. The mask can be either a clear field mask or a dark field mask, and the mask can be used in either a contact mode or a proximity mode. We do offer here at the MRL professional photomask services. If you're in need of a photomask, we do ask that you supply the data in either DXF or GDS format, and we also ask that you supply your data in microns only. We are able to achieve a minimum line width of about 1 micron. If you're interested in any of our mask services, please contact me, and I'll be more than happy to accommodate your request. Now, mask lithography versus maskless lithography. What we have here is a state-of-the-art maskless lithography on an MLA 150, a Heidelberg. Data in the form of either a DXF or a GDS file is entered into the computer. The data is then converted into information or a language that the Heidelberg can understand and generate. This enables the system to actually write here on a sample or a whole wafer or a piece of a wafer. Okay. Now, the beauty of this is the speed. Now, the traditional mask lithography, it uses a photomask being fabricated which sometimes can take up to 5 days or longer to receive, and it's limited to 1 micron features. So here's the Photomask. It's loaded into the aligner and then imaged down onto the wafer, just like the Heidelberg, but the system takes much longer, and we're limited to feature sizes of 1 micron. Right here we have an example of some images that were actually written on the Heidelberg, the maskless photolithography. Again, we have features as small as 800 nanometers. We can pattern it on a 3-inch wafer all the way up to a 6-inch wafer, or we can pattern it on pieces of wafer as small as 5 millimeters by 5 millimeters. The speed of the Heidelberg is phenomenal. Right here we have a 3-inch wafer that is written with a 405 nanometer or a 375 nanometer laser in approximately 4 minutes. A 4-inch wafer takes approximately 9 minutes. A 5-inch wafer takes approximately 16 minutes, and a 6-inch wafer will take approximately 36 minutes. And how it happens is the laser performs a light. It shines through the spatial light modulator. The modulator then transforms down to a mirror, down onto a focusing lens, and as the machine scans in X and Y direction, the image is actually transmitted down onto our silicon wafer or onto our piece of a wafer. Here you can see some of the examples of the Heidelberg, high resolution. With proper calibration and the amount of dose tests, line widths of 500 nanometers can be achieved. You can see we have a pitch of 500 nanometer line and space. Over here, it also offers a high aspect ratio. The aspect ratio is up to 1 up to 20, and this type of application is used with SU8 photoresist, and it's used for microfluidics and MEMS and waveguides. One of the advantages of the Heidelberg system is fast and high precision alignment. We can see global field by field alignment, and the alignment accuracy is better than 500 nanometers. It's fast and it's easy with the procedure that we have to align our different substrates. Also, it has the opportunity or the ability to compensate for alignment errors. It corrects rotation, offset, scaling, shearing, and allows mix and match between different tool sets. For example, if you have a typical sample that was generated on a typical MJB3 aligner, we have the ability to mix and match with the Heidelberg system so that we can match if there's any type of scaling problem, a magnification error. This system offers the ability to make those adjustments so that we have perfect alignment between die to die. Also, it has flexibility. It offers a draw mode, which gives the user the ability to add features, okay? It adds features to a patterned or previously patterned substrate. We just simply draw the features into the camera image, and then they will appear here on the sample. Also, we have state-of-the-art next generation 3D laser lithography system. This sets the standard in 3D printing and maskless lithography. It combines 2 writing modes, an ultra-precise piezo, and a high-speed galvo mode for fast structuring. We call this the Nanoscribe. In the upper right-hand corner, we can see an actual photograph that was taken of our alma mater. Here are the pictures of the alma mater that were written on the Nanoscribe using IP dip and the 63x lens. This image right here is approximately 25 microns tall. This image is approximately 50 microns tall. And this image is approximately 75 microns tall. If you look closely, you could actually see the faces of the people in the alma mater. That's how accurate the Nanoscribe system is. Here we have the seal of the University of Illinois that was written on a Nanoscribe, again, using IP dip and a 63x lens. We can see a diameter of 100 microns. This picture shows the detail of the seal that was written at a different angle And this one over here shows the detail with different luminescence. This was an actual video of the seal being written on the Nanoscribe. As it writes, we call it slices. Each slice will actually add more definition to the seal. Here are some actual photographs of some images and some devices that were actually generated on the Nanoscribe. It's very hard to see right here, but there is a nozzle about 12 microns in diameter, and it's an embedded spinneret. It's directly 3D printed into a microfluidic channel system. This device over here is a magnetic microtransporter for targeting drug delivery. Again, you can see the detail that was generated from the Nanoscribe. This particular image down here is a cochlear implant. It consists of 3D printed microscaffolds mounted onto a 2D flexible electrode array. Developing. Why do we need to develop? Well, developing shows the image transformed into a structural pattern. Developer and time found on photoresist data sheets. There are two types of developer. An MIF, or metal ion free, is for organics. If your process is sensitive to metals, we use an MIF developer, example like AZ917, and there's no need to dilute. It's a full strength working developer. Now, NMIB, metal ion bearing developer, is for inorganics. If your process is not sensitive to metals, we use an MID developer. We use AZ400K developer, and we recommend that we either dilute it 1:4 or 1:5 with DI water. Process steps. I will turn this back over to Tao. Thank you, Tao.
Thank you, Jeff. So after the developing, we can inspect the sample under the microscope. If we're happy with the sample, we can continue to do the photoresist discom and the post-bake. First, why do we need a photoresist oxygen discom? So basically, after the developing is done, there might be a very thin layer of a photoresist residue on the surface of the sample. If you don't clean that sample, if you don't clear that residue layer, there might be some challenge in the future steps of lithography or processes. So oxygen plasma here is used to lightly clean the wafer surface. It's called the discumming. So the whole process is called oxygen plasma discum. Residue has to be removed from the surface and out of any small features such as crevices or gaps. After that, the photoresist can be post-baked or hard-baked. So further crosslinks of molecules inside the resist can improve the structural stability and etch resistance. However, it should be noted that if you heat it at high temperature and bake it for too long time, although it can help adhesion, however, it may cause a reflow and the profile degradation, unless you purposely want to do that. Other processing. Okay, so basically, after the photoresist discum and the post-bake, the process of photolithography is over. However, that's not the final goal, right? We need to do some other processing steps. For example, like thin film deposition or etching. Thin film deposition will be covered in another presentation by my colleague. And here, we're not going to cover this too much. There are two methods of a pattern transfer. The first one is lift off. It's an additive process from the bottom to the top. In most cases, we lift off metals. For example, you have a substrate here. And after the lithography, you pattern the photoresist like this on the substrate. After that, you can deposit a thin film using either thermal evaporation or electron beam evaporation. And then you can see the thin film has been deposited on the substrate and the photoresist. After that, we immerse the whole sample in some type of a solvent, for example, like acetone. Photoresist can be dissolved in acetone, so the thin layer of metal, for example, gold, can be actually gone along with the photoresist dissolving in acetone, and in the end, you end up with a layer of gold thin film deposited on the substrate. This is a really nice process, especially for submicron features. For example, if you want to create a small hole of 500 nanometer, then lift-off may be the best choice. Also, it should be noted that the thickness of the photoresist should be at least 4 to 5 times thicker than the thin film to be lifted off. So basically, the key point is the film to be lifted off has to be discontinuous. If it's continuous, then you can see, you know, when the photoresist here is being dissolved, this part cannot be cleared because it is actually connected to the layer here. The other pattern transfer method is etching. It's a subtractive process from the top to the bottom. We can actually etch almost everything as long as you find the appropriate etchant. We can etch metals, semiconductors, oxide, and organics. So the process here is simple. We just have a substrate here, and we deposit a thin layer of material. We can do a sputter coating. We can do evaporation. We can do PECVD, you know, all type of deposition method, either PVD or CVD. And then we go through the lithography process, creating the photoresist on top of the newly deposited layer. And we pattern the resist, and then we can etch this new layer using the photoresist here as the etching mask. After that, the etching mask of the photoresist is gone, and we end up with a new layer deposited on the substrate. Here's the table of etchants we supply in the MRL cleanroom. It's also for the wet etching processes. MRL Fab actually provides hydrofluoric acid, nitric acid, hydrochloric acid, phosphoric acid, and nanostrip for users. We also supply these etchants to etch corresponding metals. For example, like gold etchant. It's gold etchant TFA, that's the name of the etchant. It's basically a mixture of iodine, potassium iodide, and the water. The etch rate is 2.8 nanometer per second at the temperature of 25 C. It should be noted that the wet etching is actually a chemical etching process, which means that the etching profile is isotropic, and it is a little bit hard to control, and submicron features may not be possible to obtain using wet etching processes. Here's the table of a dry etching process, and these are the tools we use for dry etching. The tools are called reactive ion etching tools, RIE. So the first two tools, they are March CS 1701 RIE system, and they are used to etch photoresist polymer graphene. And they are actually using reactive gases such as oxygen and the CF4 to etch the thin film. And the sample size here, we can actually accommodate a sample with diameter less than 6 inch. And Nanomaster NPC 3000 RIE is used to etch photoresist, polymer, graphene, and the silicon. The reactive gases used here are oxygen, CF4, SF6, and argon, and we can handle 8-inch wafer. And Plasmatherm 790 MF RIE system is used to etch silicon-based materials such as silicon, silicon dioxide, and the silicon nitride. And the reactive gases used here are CF4, CHF3, SF6, and oxygen. And we can handle wafers less than 8-inch in diameter. It should be noted that, we just mentioned that wet etching is a chemical etching. Then there should be a counterpart, which is physical etching. The dry etching process is actually a combination of chemical etching and physical etching. For physical etching, the etching profile is no longer isotropic. On the other hand, it's anisotropic. Also, the physical etching can be controlled more precisely. So when we are talking about dry etching, we can actually purposely choose which type of etching, either chemical or physical, is more predominant in the dry etching process, so that we can control the etching profile to achieve the desired etching depth and the etching shape. For example, if you want to achieve a high aspect ratio etching profile, you normally want to use a lower pressure, because the higher the pressure, the whole etching process is more like a chemical etching. So if you drop the etching pressure, you can make it less chemical, and you can make the physical etching more predominant. Another parameter you can tweak is the power. Of course, the higher the power, the higher the etching rate, and the higher the etching depth. So this dry etching process is especially useful when we are trying to achieve a sub-micron, especially like nanometer features. And for wet chemical etching, it may not be possible, as I mentioned before. However, wet etching is normally easy to accommodate, but dry etching is a little bit hard, and it's easy to control, but it's hard in terms of money, because you need to buy the instrument, right? Also, wet etching is less clean, less environmental friendly, and the dry etching is actually much cleaner and more environmental friendly. Okay, then the photoresist is no longer needed. The process is already over, so we need to strip the photoresist. There are two ways of stripping photoresist, wet and dry. It's basically the same as wet etching and dry etching. So for wet stripping, so all the organic residue is removed. And we can also use AMP or some other solvent to help, or alkaline. We can heat it up if necessary to expedite the process. Sometimes a general wafer cleaning method can also be used, for example, like RCA1 or Nanostrip. Wet stripping is cheaper than the dry stripping, and it's easier to accommodate, but it does pose an environmental impact. Dry etching is basically oxygen plasma etching or descumming. It's easier to control than the wet. It's less corrosive, it's cleaner, but it can be more expensive due to the necessary equipment. Okay, so after the photoresist is stripped, then the whole process is over. We have already covered the complete process of photolithography. However, traditional photolithography resolution is actually dependent on the diffraction limit of the UV light you use. The UV wavelength is 365 nanometers. Sometimes for deep UV, it's about 200 nanometer. If you want to achieve sub 100 nanometer features, it may not be possible using traditional lithography. So we need to turn to a new lithography method, which is the e-beam lithography. Okay, so this is the diagram of the e-beam lithography system. It's basically like an SEM. So you can see that you have an electron beam source, which can generate a finely tuned beam through the condenser lens, the beam blanker, and another stage of a condenser lens. And after the electron beam passes through the aperture, you can end up with a really finely defined beam of electrons with a very small spot size here. And then you can deflect this beam to expose the sample here. The e-beam lithography process involves the same steps as a photolithography, including spin coating, baking, and developing. The only difference is that we are actually using electron beam to expose the electron-sensitive resist, like PMMA or HSQ. Since the electron beam wavelength is really, really short, we can actually achieve a really, really high resolution and a small feature size. So in practice, the e-beam lithography system will scan the focused electron beam to draw the custom shape on the substrate surface covered by some electron-sensitive resist thin film. The electron beam can change the solubility of the resist upon exposure, enabling selective removal of either the exposed or non-exposed parts of the e-beam resist upon developing. Compared with the regular photolithography, which can only achieve a micron size feature, the e-beam lithography can be used to create extremely small structures in nanometer range. And so the pros of the system is basically nanometer feature size, say tenths of a nanometer feature size, or even smaller, high resolution and accuracy, high precision state control, and it's also maskless. It doesn't require a photomask. You just need some digital file. However, the throughput is slow, and you probably cannot work on a very, very large area. Here's the table of comparison between the Wraith E-line system. That's the one we currently have, and the Wraith EBPG 5150 system, which is the one we're expecting in summer. You can see that both electron sources are field emission source. And you can see here the acceleration voltage. It's a 30 kV for E-line, and it's up to 100 kV for EBPG 5150. As you can see that the higher the acceleration voltage, the better the resolution. So this is a significant improvement from Wraith E-line to EBPG 5150. Also, the speed of the pattern generator, it's much higher. And you can see here the minimum feature size from 20 nanometer down to 8 nanometer. And you can take a look here, the beam current. The highest beam current they can reach is 20 nanoamps for E-line, but it's up to 350 nanoamps for EBPG 5150. It means that it can actually supply an even larger dose. When the dose is higher, it can dramatically decrease the process time. And the minimum feature size, you see here, yeah, it's the 8 nanometer compared to 20 nanometer. Pattern area is almost the same, but you can see the deflection placement resolution is higher, 4 bits more. And the laser interferometer resolution is much better in EBPG 5150. The higher the resolution, or the better the resolution, the more precise you can control the XYZ stage. So therefore, you can see the stitching accuracy and overlay accuracy have been dramatically improved from E-line to EBPG 5150. Here are the SEM images of a performance test of the two Wraith systems. The top two are the SEM images done by E-line. The left one is the image of a 16 nanometer pitch grading in PMMA resist. And the right one is the optical delay waveguide written with tracks, the stitching error free write mode. And the bottom two images are done by EBPG 5150. And you can see this one, it's a test pattern with ultra high resolution lines of a 5 nanometer with 30 nanometer pitch. The pattern homogeneity is maintained over an entire wafer. And the image on the right is actually a magnified image of a gallium arsenide T-gated device. So that's all for today's webinar content. And the next Thursday, my colleague, Dr. Wasek Zweig, will have a presentation titled Introduction to Transmission Electron Microscopy. You can go to this link to sign up. Also, if you have any questions, you can email the staff, my colleague, Jeff Grau, and that's me, and another colleague, Shelley Wang, who is in charge of the major cleanroom. And tomorrow at 11, my colleague, Dr. Julio Torres and Kathy Walsh will have a presentation titled 3D Optical Profilometry. Please sign up over here. This is actually the webinars hosted by the 4 institutions across the country. Thank you. Any
Thank
questions?
you, Tao and Jeff. We have a few questions from the people here. So the first question is, why can the MJB4 make smaller features than MJB3 if they use the same wavelength and photoresist? And what creates the limiting factors on the feature size that you can achieve with them?
Well, actually, it's the way the students will actually generate the photoresist has a lot to do with it. The MJB4 is a later generation of the aligner, so that it does have the capability of going down to 1 micron. The MJB3s also can do 1 micron, but we typically favor those for anything above 3 microns because typically we were only able to achieve a 3 micron feature on our photomasks. So if we were to try to go any smaller than that, we do recommend using a different type of a mask that's generated outside of the building here, and that's why the MJB4 would be more have a better advantage to do features down to 1 micron, just because of the limitation of the mask that we're typically able to generate here.
Okay. And another question about the Nanoscribe. What materials can be written using it?
We use 2 different types of photopolymers on the Nanoscribe. We use an IP dip and an IPS. These both can be written on any type of a fused silica or a germanium or a sapphire surface. The difference in the the polymer, should I say, is the IP dip is typically used with a 63x magnification for greater resolution. The system is capable of writing down to 250 nanometers. So if you're going to be writing on any type of structure, you want to use the 63x with the IP dip. Anything larger than that, like in the 1 micron range, you'd prefer to use the IPS. And again, both can be written on, like I said, a quartz, fused silica, germanium, or a sapphire surface.
Okay. For the Heidelberg system, in order to achieve the submicron alignment accuracy, what requirements you have on the sample size and alignment marks?
Julio, they can be done on any size sample down to 5 millimeters. It's all internal. It's part of the software package from Heidelberg. You could have either a manual or an automatic alignment. Now, manual alignment will give you an alignment of approximately 1 micron between die to die. With the automatic mode, it goes down to 500 nanometers. So depending on what the operator will choose, if you want automatic, it will give you a greater accuracy between die to die or layer to layer.
So would there any reason to do it manually then?
Just for speed. If you want to, sometimes the alignment marks that the students would use, sometimes they just don't coincide with what Heidelberg wants. Heidelberg wants a typical, should I say, a cross pattern. And if the pattern isn't more or less written the way that Heidelberg recommends, the student would have to go with a more of a manual type of alignment, which is not as precise, but it will still put you within the 1 micron alignment range.
I see. So another question here is, sometimes the residue of the photoresist will remain after using the MLA. How to completely remove that? Do you have any tips for that?
Good, Tal.
Okay, I can answer this question. Sometimes the photoresist will remain there. It's normal. It normally happens when you don't expose or develop enough. So if you want to completely remove that, we normally just, to make sure that it's completely removed, we normally run the oxygen descom. So you can run at maybe 100, maybe 150 watts for about a minute or less. That should completely remove the residue of the photoresist. It doesn't matter if you're using the Heidelberg MLA system or the traditional MJB3 or MJB4 lithography aligner. As long as you don't develop it completely, that there might be some thin film there. So you can remove it with the oxygen plasma discount.
Okay. Yeah, I think that also answers the next question, which is during the wafer cleaning process steps, how do you determine that the substrate wafer is clean enough? So I'll just go to the next one. If the person that made that question doesn't wants to know more, you can always email Jeff or Tao or Shaoli for more information. So when I immerse the coated photoresist film in developer, can I remove the waste developer?
The develop gets washed away.
The developer is actually washed away, right? Because you immerse the photoresist, you immerse the sample coated by the photoresist in the developer, and the photoresist is actually dissolved in the developer. Once the developing is over, you take it out. You will find that the developer may still stick a little bit on the photoresist surface. Mm-hmm. You need to rinse it off immediately, because if you leave the developer there unattended, it's going to keep developing. So you need to rinse it off.
Okay.
I think that's the question.
There's another interesting question here. That is, can you do both? Can you use both on the same sample? So match the wraith lithography for smaller features on your sample and with the optical lithography? And does it matter which one you do first if you can do that?
Of course, you can match the two lithography techniques together. No matter which one you do first, you just need to make sure that you got the right alignment mark. Mm-hmm. And I would say that you can try the optical lithography first and normally create larger features. And for example, on the Heidelberg system, and you create optical alignment marks, and then you can coat some gold thin film on top of it. When you go to the raised system, because gold really looks bright, in the SEM, so it's easy for you to find an alignment mark and run the lithography on top of that. Basically, you're just using the alignment mark to match two layers of the patterns together.
Okay, so we're pretty close to our finishing time now. So I'll direct other people that have a few more questions to directly email Jeff, Tao, and Shaoli. So the email is there on your screen. And thank you everyone for coming and seeing this webinar. And thank you, Jeff and Tao, for a wonderful talk.
Thank you.
Thank you.
I don't know why that video didn't